Hello everyone, as you know, my name is Daniel Fernandez. I am the owner of scienceinhydroponics.com, and today I am re-recording a video that we did before on plant uptake and the effect of plant uptake on roots on pH. And I'm doing this because there was a very big mistake on one of the tables. So a lot of the values were off by a factor of 100. So I am going to be redoing the video, fixing that mistake, and hopefully I'll add a few things to this video that will make it worth the rewatch. So if you already watched the previous video that had the mistake, please watch this video so that you can see how the mistake was fixed, and I'll also explain why the mistake happened. So in this video we are going to talk about how plant nutrient uptake affects media pH. So if you remember, the pH is defined as minus the logarithm of the concentration, of the molar concentration of what we call hydronium ions, which are these H3O plus ions. The molar concentration, so the amount of moles per liter of water. So in a sense, plants will always affect pH by changing the concentration of hydronium ions in the media. So we're going to see why they change the hydronium concentration and how these changes happen. So let's start by talking about nutrient uptake in the plants. So most of the nutrients, the macronutrients, nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur, all of them have charges. So nitrogen is present as either nitrate, minus, or ammonium ions. Phosphorus is generally present as dihydrogen phosphate anions. Potassium is present as potassium cations. Calcium is present as potassium plus 2 cations. Magnesium is present as magnesium plus 2 cations. And sulfur is present as sulfate anions. So, as you can see, all of them are charged. And the fact of the matter is that if you take a charge out of the solution, you need to do something to preserve the charge balance, because you cannot leave a solution without a charge, because that will cause the buildup of a potential between the outside and the inside of the plant. So let's say we have here the plant. We have here inside the plant and we have here outside the plant. So let's say that outside the plant we have something like a potassium ion, and the plant wants to take this in. When the plant takes this in, we leave a positive charge hole outside the plant. So we need to make up this positive charge. The plant will make up for this by exchanging this potassium for a hydronium ion. So you can see here how getting a potassium inside the plant means that we need to push a hydronium outside the plant. And since now we have more hydroniums outside the plant, we have here that the pH will decrease, because the more hydroniums, the lower the pH, because it's the negative logarithm of this concentration. Now, we can also have a case where an anion is taken in. For example, let's talk about the nitrate anion. Let's suppose the plant wants to take this in. If the plant takes in an anion, then we need to replace a negative charge. However, you could think about something like an OH minus going outside, and this would balance this negative charge. And this OH minus would raise the pH, and therefore we could think that this causes the pH to increase. In reality, this scenario is not very common, and what happens is that the plant will take in a nitrate, and then it will also basically deplete a hydronium as well. So it will take up this nitrate and then it will compensate by taking a hydronium. Also, more commonly, the plant might also basically discard the conjugate base of an organic acid, like for example an acetate with a negative charge, and push this outside. So all of these scenarios cause the same effect, which is that the pH will increase. So we have here cations, when they are taken up, will drop the pH because the plant exchanges cations for protons. And then here we have that anion uptake will increase the pH because the plant will exchange an anion for either a conjugate base of an organic acid or will also uptake a hydronium to balance the charge. In any case, the uptake of an anion will always raise the pH. Now, if you have something like a magnesium that has two positive charges, then the uptake of this magnesium requires two of these to be taken out, because we now need to balance two positive charges that went in. So the higher the charge, the higher the effect of the uptake of an atom has on the pH. And the fact that we are talking about here about single atoms and molecules means that we need to not talk about the mass of these things that we have here, but about their molar concentrations. And this is why we are going to talk about molar concentrations, and even more, we are going to talk about the equivalent concentrations. The equivalent concentrations, which we also refer to as normal concentrations, are basically the molar concentrations times the charge of the different atoms. So one equivalent of, let's say, potassium and one equivalent of magnesium will basically be twice the molar concentration of the potassium. Will be half, the molar concentration of the potassium, because the magnesium has double the amount of charges. So this allows us to compare apples to apples, because we would be comparing equivalents in terms of charge and in terms of moles. Okay, so now that we have discussed the exchange of nutrients and how these affect the pH, we are going to be talking about how the amounts actually affect the pH of the media. To talk about that, we need to talk about the tissue that the plant is trying to build. Here, we have the amounts for the different macronutrients. We have the percent dry weight of a tomato leaf. So you have here the different composition in percentage terms. You see that a tomato leaf is 4% nitrogen, around 4% potassium, 0.4% phosphorus, 2% calcium, 0.5% magnesium, and 0.8% sulfur. Now, the molar masses of these elements is substantially different. And you can see here that nitrogen has the lowest mass. And this means that this 4% involves a much larger number of atoms than this 4% of potassium, because potassium has a molar mass that is more than twice as large, which means that an atom of potassium is significantly heavier than an atom of nitrogen. So this 4% is much more significant in terms of number of atoms in the case of nitrogen versus in the case of potassium. Now, this is where I screwed up last time, because I did a conversion wrong, and in the previous video, you will see that I referred to this amount here as millimoles per kilogram, as 28 millimoles per kilogram, and this was wrong. So these are the correct values in moles per kilogram of dry weight in tissue. So we have basically converted these values to moles per kilogram instead of percent in a kilogram, using the molar mass here and these percent values. And you can see here that nitrogen is by far the largest. We have 2.8 moles of nitrogen per kilogram. So a lot more atoms of nitrogen than we have atoms of potassium, which is the next atom that we have the most of. And then we have substantial amounts as well of potassium and magnesium. However, when we take these two equivalents per kilogram by basically multiplying by the charge, we see that this calcium number becomes much more meaningful, while the potassium and the nitrogen numbers remain the same. Now, we can basically see the effect of pH that this has on pH by looking at the sum of these things. So what is the sum? what is the sum of the cation equivalents and what is the sum of the anion equivalents. And I'm gonna call this A and I'm gonna call this B. If A is greater than B, then the pH will go down because we have more cations than anions, and when we take cations, the pH drops. So if A is greater than B, the pH will drop. And then in the other case, if B is greater than A, then the pH goes up because we have more anions getting uptaken than cations being uptaken in terms of equivalence. So when we look at the sum of cations here, we see that the sum of cations is 2.43 equivalents per kilogram, while the sum of anion equivalents per kilogram, sorry, I carried out these milliequivalents. This is wrong. So while the number of equivalents per kilogram is 3.48. So we have way more anions than cations, and that is because we have way more nitrogen than we have cations. And when we add everything, when we add the cations and the anions, we see that the anions, because of the nitrogen, have a much, much bigger effect. And then the difference in equivalents per kilogram is 1.05, which means that we would basically need to add 28 milliliters of 98% sulfuric acid per kilogram of dry tissue to compensate for the increase in pH that this would cause. And this is why when plants are creating leaf tissue, they will tend to increase the pH, because this anion uptake, we have B is much greater than A, and this imbalance means that the pH will increase very aggressively. You can also see here a graph where you can see how big this difference is in terms of equivalents per kilogram. Nitrogen is massively required to create leaf tissue, and this creates this big imbalance. Now, you could think that reducing the nitrogen would reduce this problem, but as a matter of fact, we don't want to do this because we actually want for the plant to create this tissue. So under healthy circumstances, the plant should be increasing the pH of the solution because the creation of this leaf tissue demands that the plant increase the pH. If we were not creating tissue of this composition, but let's say we add a lot of potassium and calcium so that we can push these numbers up, then the tissue might not be healthy or might not be efficient in terms of fertilizer usage, because we know that we can get healthy tissue with this composition. While if we lower the nitrogen to try to get this number closer together, we might create tissue that's nitrogen deficient. So this goes to show that a healthy uptake can cause imbalance of pH, and we therefore absolutely need to be adding acid, for example, in a recirculating system to correct this from happening. Now, on the next video, which will be coming out soon, we will discuss one way in which we can fix this using ammonium when we're talking about the growing of leaf. And we're also going to be talking about how this changes when we're growing something that is not leaf, but for example, tomato fruits. How does this relationship change when we change from growing leaf to growing fruits? And we're also going to talk about how we can buffer pH in that particular case. I hope you enjoyed this video. I apologize for the mistake in the previous video. I hope this video was clearer and communicates the point better. If you notice any mistakes in this video, please comment, and hopefully I won't have to re-record it again, but I will if necessary. Please remember to like and subscribe. I'll see you on the next video, and bye-bye.